When we talk about solids, liquids, and gases, we need to understand that when you have a solid, the particles of a solid have very fixed positions, and there's very, very little motion. There's some motion of vibration, but there must be some very strong attractive forces between molecules within a solid, as opposed to when you have a liquid, those molecules can move past each other. And as they can move past each other, then the attractive forces between those molecules must be significantly less. And then by the time you get to a gas, the particles of gas are so far apart, they're moving randomly and rapidly. The attractive forces between these gas particles is practically zero. And so if we want to know why is something going to be a solid or a liquid or gas at room temperature, we have to get a sense of how strong are the attractive forces. So for example, for something to be a gas at room temperature, it would most likely have weak intermolecular forces. And so in summary, we can basically say that solids have very strong attractive forces. They're held together very closely. They're highly ordered. There's little space between those molecules, and there must be very strong attractive forces. Liquids have some strong attractive forces, not as strong, of course, as solids, and this allows them to flow easily as we look at those molecules or those solutions. So what actually happens to the molecules and the attractive forces when you apply heat? So if we take water as an example, there's an attractive force between the oxygen and the hydrogen. And we know this is because water has a dipole. And so we could say, well, there are going to be dipole attractions. And what we also want to do is to say, well, actually, is this a special case where hydrogen is directly bonded to NOF? And in this particular case, in the case of water, hydrogen is indeed bonded to oxygen, hydrogen bonded to oxygen, and because of that, this is a special case of hydrogen bonding. So we know that in this particular case, the intermolecular force are hydrogen bonds or hydrogen bonding. And when you add heat to this to these systems, what happens to the molecules? Well, nothing really happens to the molecule, but we overcome this attractive force. This is the most important thing to realize. This attractive force is what gives us the physical properties, because the water molecule in ice and in water, liquid water, and in steam is still the H2O molecule. And so you overcome these intermolecular forces. And so if you have less energy required to overcome these intermolecular forces, it's a much lower amount of energy than it is to break the actual covalent bond, to break apart the water molecule. And that's why we always see the water molecule in the solid form, we see the water molecule in the liquid form, we see the water molecule in the gas form. And what we've done to get between those phases is we've just overcome the intermolecular forces. So the important thing to remember is that covalent bonds are much stronger than intermolecular forces. And so we just needed some definitions. If we're going to take a solid and we're going to turn it into a liquid, the temperature at which this occurs is the melting point. The process of a liquid becoming a gas is vaporization. So melting point, boiling points, those are temperatures at which phases change. So for example, boiling point is the temperature at which the liquid escapes and becomes a gas. The process of the liquid becoming a gas is vaporization. So it's important to keep those things separate, that one is a temperature and one is a process. So for example, when you take a gas and you turn it into a liquid, that's called condensation. If you take a liquid and you turn it into a solid, that's called freezing, and it occurs at the freezing point. Now, the important thing to remember as well is the freezing point is the same as the melting point. And when a gas goes directly from a solid to a gas, this is called sublimation. And so we can summarize that by looking at, if we look at what happens when you take some type of solid and you heat it up. And so it's worth knowing this this graph. So on the y-axis, we see that we have increasing temperature, and on the x-axis, we have increasing energy of the sample. So what we're doing is we're adding heat to this sample. And so at the beginning, we have a solid. Here's our solid. And as we add energy to it, the temperature increases. No surprise, here it is, increasing temperature. We know that if we add heat to, let's say, a block of steel or a pan on a stove, as you add heat to it, it starts to get hotter and it starts to get hotter. And if you've ever melted chocolate in a pan or in a double boiler, you know that as you heat it up, it starts to get warm and it starts to get warm, and then you just sort of sit there for a while waiting and waiting, and then suddenly it melts. And so the important thing to realize, as you add heat, it heats up, and then you keep adding energy to the system, and during that time, the temperature doesn't actually change. And that's the point at which melting occurs. And so when you boil water, as an example, you take liquid water and you add heat, it gets hotter and hotter and hotter. And then there comes a point where you just wait for the bubbles. And as you do that, you keep heating, you keep adding energy, but the temperature doesn't change. Because once we get to the boiling point, we keep adding heat, because if you want to boil water, you have to keep adding heat. You don't get to 100 degrees and then suddenly miraculously it just boils. You have to keep adding heat to the system, but the temperature doesn't change. And so the question is, well, what's happening to all that energy? Well, during melting and during vaporization, or liquid going to a gas, there's a large amount of energy that's put in. And that large amount of energy that's put in goes to overcoming those intermolecular forces. Because at both of these stages, what you're going to do is you're going to overcome the intermolecular forces that are keeping those molecules together. You don't break the molecule because the molecule still stays intact. So again, up here, this is the water molecule, this is the water molecule, this is the water molecule. But the attractive forces are overcome. And that's why, as you increase the amount of energy you put in, the temperature doesn't change. Because during this period here is where you're overcoming these intermolecular forces. During this period here, you're overcoming those intermolecular forces. And so hopefully you can see that if you have very strong intermolecular forces, this line or melting point is going to be higher. This boiling point is going to be higher if you have stronger intermolecular forces. And so we need to really have a good understanding of what those intermolecular forces are. And so you can also go directly from solid to gas, and this is called sublimation, and you bypass the liquid. So carbon dioxide is the best example, where you go from a solid and you can end up at carbon dioxide gas very quickly. Then you can also have a gas to solid deposition. So here, for example, these are ice crystals, often formed at night in the fall and in the winter, where you have a large amount of moisture in the air, which is present realistically as gaseous CO2 or very small water droplets, and you can get that deposition to a solid ice formation. And so when we talk about intermolecular forces, these are all to do with molecules. And intermolecular forces and states of matter, whether it's a solid, liquid, or a gas, are intimately involved. Now, the most important thing to remember about intermolecular forces is they occur between molecules. If you have an ionic compound, and just to reiterate, that is typically a metal plus a non-metal, the only exception being the ammonium ion. If you have something between a metal and a non-metal, which is a cation, the positive one, and an anion, the negative one, they're both charged, and the bond between those, so if we take sodium chloride, the attractive force that we have here, this attractive force is not an intermolecular force because it's not a molecule. It's an ionic compound, and this attractive force is an ionic bond. It's not an intermolecular force. And ionic bonds are the strongest forces that hold matter in a solid form. So if you have an ionic bond, it's going to be so much stronger than any intermolecular force that we can think about. So when we talk about intermolecular forces, we must be talking about molecules. Okay, and if we have dipoles in a molecule, we're talking about dipole-dipole attractions, because these oppositely charged ends will attract each other. And so in order for a molecule to be polar, and this we go over in lab next week, is in order for a molecule to be polar, two conditions must be met. One, it must have polar bonds, which is no surprise. And two, the bonds must be arranged such as that there's a separation of charge exists. And so when we talk about that, we want to make sure that the polar bonds that we're looking at, for example, hydrogen and chlorine, it's a polar bond. The molecule itself is polar because there's going to be a negative end and there's going to be a positive end. And so what we need to do is to realize that these are the molecules that we need to understand if they're going to be polar or non-polar. And these intermolecular forces are just electrostatic attractions between something positive and something negative. And so you want the molecule to have a positive end and you want it to have a negative end. And if you can do this, then we know what intermolecular forces are going to be present. And there are three types that we talk about. And this is between neutral molecules, because if they were charged, they would be called ions. And if they were ions, they would have ionic bonds. So that's a totally different type of attractive force. What we're talking about here is just neutral molecules. And there are three of them. There are dipole-dipole attractions, there are hydrogen bonds, and then there are what are called London dispersion forces. And in some courses, biology, people often refer to them as van der Waals forces, but they're all the same thing because there are multiple names for the same things depending on who came up with the initial idea. And so what we now need to do is to be able to understand, well, which one of these three attractive forces exist, and in order to do that, we need to think about what those molecules are. And so, just to reiterate, the one that we see quite often is hydrogen directly bonded to NOF, and that is this additional attractive force called a hydrogen bond.